When animals get together in large numbers, they often move in a very weird way. Starlings might be the most famous for it. Their individual swoops translate to massive undulations across the entire flock, making the whole thing look choreographed and hypnotic. But birds are not the only animals that move in this way. Schools of fish, swarms of insects, and dense crowds of people can display impressive coordination too, which makes these mesmerizing patterns a tantalizing topic for the scientists trying to figure out exactly how they work. And not just so they can explain why animal swarms look like that, or help design buildings with safer layouts, some of this research has even wound up in a famous Hollywood movie. When starlings move in those weird flocks, it's called a murmuration. And murmurations are just one example of an emergent behavior, where each individual in a flock acts according to its own motivations. There's also an entirely different collective behavior that arises in response to all those individual actions. You're an emergent system, turns out. It's a bunch of cells working together, and you have thoughts about how you have to pee and are stressed. To get up tomorrow. Now, since the movements of any one bird are fairly predictable, you might think scientists can just extrapolate to predict what shape the overall murmuration will be at any given moment. But no. There's a bunch of unpredictable chaos mixed in with all that determinism. As such, physicists have become obsessed with emergent behavior and have created an entire subfield devoted to it called active matter. It's clear that individual birds are communicating with each other, like somehow, to coordinate the motion, although exactly how is left for biologists to figure out, so we'll set that aside for now. Don't worry, biofans, we will be back for you. Kind of like a game of telephone, the starlings seem like they only communicate with their direct neighbors, but unlike you experienced back in grade school, the message they're passing along can make it across the entire flock without getting garbled. But what kind of messages are being sent, and how far can they travel between individual birds? It's time to break out the mathematical models. So let's start with some basic behavioral rules based on real-world observations. First, individual birds avoid crowding their neighbors. And second, an individual doesn't want to be separated from its flock. And third, individuals tend to end up facing the same direction as their neighbors. Each bird also has a limited range of visibility, so let's assume each individual in the flock can only see its neighbors within a couple of body lengths of itself and within a specific angular range. Back in the 1980s, a computer scientist named Craig Reynolds used a similar set of rules to model what he called birdoid objects, or Boids for short. Although technically it was not just meant to model birds. I love this, Boids. They're Boids. The resulting algorithm was initially developed for use in computer animation, and by 1992, it was ready for its silver screen debut, modeling flocks of penguins and bats in the movie Batman Returns. I told you it was a famous Hollywood movie. The Boids algorithm has been pretty successful at replicating emergent behavior in flocks, such as how small flocks of Boids merge to form larger flocks, and how a flock can split to avoid an obstacle like a tree or a predator. And for more accuracy, you can even program your Boids with a migratory urge, an ingrained preferred direction inspired by a real-life bird's biological urge to fly south for the winter. And I'm going to tell you more about this, but much like a basic cable showing of Batman Returns, we do have to take a break.
This SciShow video is supported by Zocdoc. Zocdoc is a free app and website where you can search and compare high-quality in-network doctors and click to instantly book an appointment. Our senior staff writer, Emma, used Zocdoc when she moved to a new city. She needed to find a doctor close by that takes her insurance, and she didn't want to deal with the hassle and exhaustion of calling a bunch of doctors to find someone to fit into her busy schedule. When you're in a new place and busy with other stuff, not knowing which doctor to go to can be a big hurdle. It can be overwhelming and hard to figure out where to start looking for a doctor or if they'd even be a good fit. That's why Zocdoc has patient reviews that you can read through before you get too invested and waste a bunch of time. You can book in-network appointments with more than 100,000 doctors across every specialty, from mental health to dental health, primary care to urgent care, and more. Plus, you can choose how you want to meet them, in person or through a video visit, whatever works for your life. Zocdoc made it easy to find exactly what Emma was looking for, and they found options that didn't have a 6-month waiting period. Incredible! So you can stop putting off those doctor's appointments and go to Zocdoc.com/SciShow to find and instantly book a top-rated doctor today.
There's a lot the Boids algorithm still can't account for. It's a purposefully oversimplified version of reality. You can tune the rules and parameters within the algorithm, like the visibility range or repulsion and attraction forces between the individual Boids. Eventually, you'll get simulation results that mimic different animal swarms in the real world and their emergent behavior. And by tweaking the model properties, scientists can inch toward figuring out how individuals might sense and respond to their flock mates and environment. But at the end of the day, they're really just inferring rules that seem to work and recreate the emergent properties of a real flock. There could be lots of other parameters physicists aren't accounting for, and there are often multiple combinations of input parameters that lead to really similar simulation outputs. But let's give the physicists some credit. They aren't only guessing. They've taken measurements of birds, fish, and insects to see how individuals influence each other, allowing them to identify and tune flocking simulation parameters. For example, analyses of starling murmurations revealed that while the birds only interact with their nearby neighbors, information still makes it across the entire flock. So if simulated flocks can also communicate across the whole group, then the model is on the right track. Meanwhile, studies on groups of 3 fish versus shoals of 30 fish have found that the fish likely receive signals from their closest neighbors and their flock mates that are farther away. So adding more complicated terms to flocking models like the Boids algorithm could improve simulation results. But despite all these insights, they're still just simplified rules that describe and reproduce flock phenomena. They can't account for all the complexities of animal behavior, like individual motivations or decision-making. And we do have to be careful not to anthropomorphize these animals by assigning them goals or hopes and dreams, unless they're the ones in Batman Returns, clearly did have goals. So on the other side of the emergent behavior problem, biologists are considering the neurobiology of how animals navigate. Instead of defining rules that the animals follow, biologists have successfully simulated flocking behaviors by modeling how animals encode spatial information in their brains. Physics models, like the Boids algorithm, assume actions depend on where an individual is positioned relative to its neighbors. That's considered an egocentric way to navigate. But biology studies have shown that basically across the board, animals also navigate in allocentric ways, meaning guided by external things in the landscape. Egocentric and allocentric navigation are stored differently inside the brain, and the allocentric flocking model suggests that when some animals swarm, they're rapidly switching between egocentric and allocentric methods. This means animals can probably sense where their flock mates are relative to themselves and relative to the landscape and any nearby predators. This combination of self-centered and landmark-oriented navigation could be the biological key to producing emergent swarm behaviors. One paper from 2025 has shown that models of this random, rapid neurobiological perspective switching can successfully recreate swarming behaviors without needing to infer rules like what happens in the Boids algorithm. These two different perspectives have brought us closer to understanding animal swarms, but physicists and biologists will need to keep working together to understand active matter. Because animal swarms aren't the only systems governed by active matter principles. Self-propelled robots, though not alive, act individually according to fixed rules, and much like starlings, they can display completely different collective behavior. For example, these tiny hexbug robots that can turn a gear. On the living side of things, cells collectively migrate during biological processes like embryonic development or wound healing. This emergent motion is completely different from the motion of individual cells. And don't forget, humans are animals too, but with even more complicated decisions to make, like whether or not to go see the Batman movie marathon at your local theater. So active matter has also been useful for modeling human crowds. Using similar rules as the Boids algorithm, physicists have created models to describe how people cross a crosswalk, form a mosh pit, move through an exit, and create dangerous crowd crushes during moments of panic. If we can design around that, we can prevent unnecessary injuries or worse. Turns out those Boids are pretty flockin' useful.